One idea for defeating this is what's called a trust function. And you can say, well, I'm going to have some way that I weight these donations so that if I'm sure that someone is a real person, I actually count their donation. Whereas if I have a bunch of new people showing up that I don't know anything about, then I may not trust them as much. I may discount their donation when I do the calculation so that people I already know are more likely to be giving to legitimate grants. And of course, that has issues as well. Especially the European Union courts have ruled, if your algorithm is discriminating, it doesn't matter whether that discrimination is an intentional part of the algorithm or not, you're still liable. So you have to be careful with a trust function. It's not in any way based on anything that would be considered discriminatory. Now, with that said, a trust function is a great solution. If you have a trust function, it will solve your problem. The question is, how do you design a trust function? And this gets into a question we rarely ask, which is, in our Calculus 1 classes, we could say, like, how do you make a function that has these properties? And make our students come up with that, which is something people have to do in the real world. Another scenario that's undesirable is you could have people who realize my grant is not very popular. So if I look at users B and C, and each of them has more resources than average, and each of them is basically invested in one particular project, they would get better results if they worked together and agreed to split up their donations. So you can do the math and you can look at the total matching that 2 will get, the total matching that 3 will get. It will be better under this scenario than if each of them had just donated one amount. Because again, quadratic funding is designed to make it so that more popular projects get a larger portion of the matching pool. An approach to defeating collusion is that you can make what's called a pairwise penalty function. And here you're going to look for users who made all of their contributions to the same sort of family. And if you get a situation, you realize, wait a minute, B only gave to the same grants as C. You say, I'm going to discount both B and C's contributions when I do the calculation. That's the setup. We have quadratic funding, which is a mechanism that promises to change the way that certain economic resources are allocated. And we have these two situations where it can essentially be gamed. One is the Sybil attack. The other is the collusion attack. And in both cases, the problem is people are they're signaling something that isn't their true legitimate interest. And so because it's deceptive, that's why we consider it an attack. Token Engineering Academy research group on GitCoin grants consisted of me and several other people. I was the only pure mathematician. There were engineers, computer scientists, data scientists, economists, a wide variety of people. I'm going to talk about some of the solutions that we achieved. There are 3 issues, right? One is we can still have a large donation, and just one user with that large donation can get lots of funds. They don't get as many funds as a large group of small donations, but they still can essentially rob the pool. We also have collusion, we have Sybils. And so because of this, there have been some modifications made to the original quadratic funding algorithm, and each of these will attempt to fix some of these issues. The first is we have this situation where B is donating money, but they're the only person interested in their grant. How do we know that this isn't just a ploy to get matching funds back? Because I could double my money, essentially. If I just had a project that was give B money, the algorithm is going to give me matching funds. So to avoid that, we subtract off the original donation. So that if B donates $3 and no one else gives anything, that $3 doesn't get matched. It's treated as $0. And the only way your funds get matched is if at least one other user donates money to the same project. And so you do that by taking your original formulation here, where we took the square roots, added up and squared, and you just subtract off the original donations. And then we're going to throw on some scaling constant K just to try to keep the things from becoming huge. But the real fix here is that we're subtracting off the original donations. So this makes it impossible to create a give myself money grant, because now if I'm the only person who cares about this, I won't get anything. This modification, if you think about going back to high school algebra and actually distributing or foiling things out, you can sort of see what's happening here. I'm distributing out each of these things. And the green is my original contribution that's getting subtracted off. And the yellow is what I'm actually left with. So if I expand this out, then when I square it, I get this expansion. And when I subtract the original, this is the end result of the formula if I were looking at 3 users donating. You'll notice something. This looks a lot like a symmetric function. It's essentially a symmetric function just with square root. And this geometric interpretation is really helpful to people. To be honest, most people would rather look at this and get more intuition from this than looking at this. We drop the 2 because it gets absorbed into the constant. And so what this really emphasizes is that you're looking at interactions between users. And this is how mathematically the idea that we should have a broad community of support shows up, because the more people give, the more of these pairwise multiplications you have, the bigger the donation is. If we look at collusion, how would we address that? So the suggestion of Vitalik Buterin in his blog post is to impose what's called a pairwise coordination penalty. And so basically, instead of having a single constant, earlier we had a single constant k, we're going to make this a constant that depends on which pair we're looking at. And the constant, which I guess isn't really a constant if you're changing it based on each pair, but this modification multiplier that the users have in common. It's essentially a dot product that calculates the angle between the two users in terms of their contributions. So how do we actually calculate this? Well, we define the coordination coefficient as the inner product. If you think of this as a bipartite graph and look at the bipartite adjacency matrix with the weights, this is just the row by row inner product. And so if I look at a situation where I actually have these bipartite graph, this donation setup, you can look at this as vectors, right? Each user defines a vector where the entries of the vector are the contributions that they've given to the grants. And so then to define this coordination coefficient, we just take the inner product. And then you take that coordination coefficient and somehow you use it to calculate the coordination penalty. And so Buterin's suggestion is you take a function of this form, where this is the inner product between the user contributions in the matrix, and R is just a constant. GitCoin, at least when I did this research, uses the constant R equals 1. So this is just 1 over 1 plus this inner product of the contribution vectors. And then you multiply by that, which is essentially, if you look at, I'm multiplying this by my product of contributions. Well, the larger that this gets in the denominator, the less that contribution matters. So if you have people who have contributed exactly the same way on 100 projects, we're gonna discount their view because they're essentially clones. This discourages collusion. It doesn't eliminate it. B and C can still work together, but if B and C only give to the same project, then they're gonna see their donation weights lowered. Without this pairwise coordination impact, then each of these grants would get a score of 2.5 if you do the calculation. With the pairwise coordination impact, when you calculate through here, and you can see this inner product in the bottom, then each grant would get a score of 0.41. So it does significantly lower the donations of colluders. What this does is that if colluders are trying to affect a single grant, this is going to actually place a bound on how much money they can extract through collusion. What about a Sybil strategy? What do we do here? Well, in practice, in GitCoin grants, the strategy was to use a trust bonus. And you allocated this trust bonus based on some evidence provided that the person was actually a sentient being. So for instance, if you had a Twitter account with lots of posts that you could verify was yours, or if you had a lot of GitHub contributions, or if you had been a member for a long time, something that was difficult to fabricate, essentially a proof of work, if you think about it. If you give people with higher trust bonuses or people with lower trust bonuses, if you change the weight of their donation accordingly, this does something to mitigate against a Sybil attack. So these are the three problems, and these are the three potential solutions. So when you look at this in the final formula, we're going to use the donation for a grant G. We're going to let GI denote the amount given by user I to that grant. And so the formula for the actual matching amount can be calculated this way. But notice again, up to some potentially changing constants, this is still a symmetric function, just with square roots. And so if we didn't have these constants, this would be an honest to goodness symmetric function. If you think about it this way, you can ignore the messy constants and you can just look at it as the trust of the verified user over 1 plus the pairwise coordination times this, and it makes it clearer the symmetry that's happening. And then if you look at a set of grants, then it's just going to be applying this formula over all of the potential grants in the collection, because grants might be working together to try to extract funds from the system. There's a bit more to it than that in terms of the actual software implementation, but mathematically, that's the idea. We have a function that takes as input the donations of each user to each grant and then calculates their matching funds based on this formula. So that's a good place to stop and see if there are any questions about what I have said so far.